So we're into our last reaction, and our product will be our last family. We're going to make esters. So we're going to learn the reaction and how to name the product. So this reaction should jump out to you. We've got an organic compound, a derivative, with another hydrocarbon derivative. It's the only time we've seen anything like this. You have to be a little careful though, because alcohols can do elimination with acid catalysts. But this is an alcohol with a carboxylic acid reactant. The carboxy group, C double bond O H, that can react with a hydroxyl group. Again, not a hydroxide like we saw in elimination, hydroxyl. So I have a dash from the O to some hydrocarbon. Okay. The products of this reaction are an ester that we need to talk about once we see one made, and you need to not forget your water. It's easy to miss, and I have to make sure I don't miss it when I do the reactions. Now, you do need a strong concentrated acid as a catalyst. When you do this lab, if you make an ester, you've got to remember to put in your sulfuric acid or the reaction won't run. So to see this in action, I'm going to react propanoic acid with methanol. I'm going to color code it to help the understanding. You obviously don't have to color code it on an assessment. So we have propanoic acid, and I want to put that carboxy group towards where I'm going to write the alcohol so I can show the reaction. So 3 carbons with the functional group we need. That's going to react with methanol. That alone isn't enough. We need the addition of a strong concentrated acid. Okay, the carboxylic acid is too weak to act as a catalyst itself. Now, you don't need to know how this reaction occurs, but I'm going to show you the first, or one of the steps. I'm not doing the full complete order. A university professor will go into much more detail and be a little more correct than I'm going to be. Okay? But this connection helps make sure you get the right product. Okay? You've got lone pairs in that oxygen, 2 of them, which are negative. And this bond, I'm going to erase that, is very polar. That carbon is the positive end, and the oxygen is the negative end. That'd be sort of Chem 20 using electronegativity. They're the numbers right above the elements on your periodic table. Carbon has less pull to electrons. So the negative electrons can be attracted towards that carbon. And this is the connection you need to know. It's the alcohol O to the C on our acid. So I'm going to draw that connection. That's going to make our ester. So there's those 3 black carbons. I'm going to fill in all the H's that don't move. Okay. The double bonded O is going to stay in its place. But I connected that red O to the black carbon. Then that red oxygen has 1 carbon connected to it. So there's our color-coded product. Some things were eliminated or removed from our organic compounds. We have this OH ends up breaking off. When we add the red O, we've got too many bonds in that carbon, so that OH comes off, and this red H comes off in the attachment. Okay. So again, this isn't the perfect sequencing, but I'll leave that to a university professor to go through. The catalyst helps this. Now those pieces that I've blue underlined together, we got an OH and an H, that's our water product. So it's not necessary in this course, but it's quite useful to connect the alcohol O to that C double bonded O to make sure you make the right product. So this we call an ester. We haven't seen anything like this before in this course. We've got a bunch of carbons, we've got an O and then a carbon. We've never seen something in the carbon parent or stem before. And we'll deal with the naming shortly. But we're going to name to the both sides of the O to name this ester. So that's the balanced reaction. I've got the water, I've got my ester, and I have my two organic hydrocarbon derivatives. These are always one ester being made. You don't have to worry about things adding two ways or two names. So you'll see another example of this, but let's talk about how you name that ester. Okay, how you name the black part and how you name the red part. So naming esters, and fairly soon you're going to be practicing drawing the reactions and naming them. Okay. So the ester gets its name from the reaction that made them, the acid and the alcohol. Now, UPAC makes the rules, and they've said that we have to deal with the alcohol part first in the name. It could be on the right side of the ester or the left side, we don't care. We're going to use the alkyl name from that alcohol. So that'd be like methyl, ethyl, propyl, butyl. UPAC says we deal with the carboxylic acid part second. That's the piece that has the double bonded O. Okay. We're going to use the alkane name from the stem of the acid. Drop the E, that's something we've done before. Add a family name. We're going to add O8 for esters. So I'll do a second reaction example and I'll name the product this time. So I'm going to draw those two reactants. I'm going to color code them. Ethanoic acid. Eth is two carbons. We never have a number with carboxylic acids because they have to have that carboxy group at the end. So we don't have to tell the reader that with a 1 number. Propane 1-all. 3 carbons. And we're only going to learn how to name primary alcohols when they make esters, where the hydroxyl group is at the end. I'm going to stick our hydroxyl group close to the carboxyl group so I can show my arrows connecting the two reactants together. After I switch colors. I'm going to leave the plus out. It would kind of be in my way, but typically would have a plus between the two reactants. We need a concentrated strong acid. Sulfuric acid is really common and likely to be used in any ester lab. So it's the O from the alcohol that connects to the C next to the carbonyl base C. Carbonyl is C double bond O. So there's our alcohol, and it's going to connect to the C of the carbonyl. So let's draw that. So we've got black carbon to black carbon. The right-hand black carbon has the double bond O. The black OH is going to come off, be part of our water. Now we're ready to put the red O, and that red O has 3 carbons attached to it. And all of those carbons are filled with hydrogen. Oxygen has a bonding capacity of 2, carbon 4, and I have completed my structure properly. I need to not forget the water. I'm not color coding that because it's one black H, one red H, and a red O. So that is the reaction. Now we're going to name it. When it comes to naming it, you kind of have to find that O and look to both sides. One side came from the alcohol, one side came from the acid. You deal with the alcohol piece first, no matter whether it's on the right or the left. So the alcohol piece doesn't have the C double bond O. So the alcohol piece I have in red, and the carboxylic acid piece I have in black. But even if you didn't have the reaction, the C double bond O is your clue to the acid piece. Okay? And it's going to be next to the O in the chain. So I have to deal with the alcohol first. That's the red. I'm just going to use ethyl methyl propyl butyl to represent the alcohol. 3 carbons, so that's propyl. That tells the reader we've got an O in the middle and then 3 carbons. Then we move to the carboxylic acid. That's 2 carbons. So we're going to use its alkane name, ethane, but don't put the last E, and add O8 to tell the reader we have an ester. Okay. This O8 tells us we have this kind of linkage, C double bond O from the alcohol to an O, and then going on to a carbon. That green circle is sometimes referred to as an ester linkage. Typically what you see on tests or diplomas is often you'll see a picture with the alcohol piece on the right to make sure that you know to name the alcohol piece first, to put that on the left part of the name. So that's our esters. So we've got a family, the ester, okay, we got a reaction is esterification. So that reaction type I put in your notes there. So we have addition, substitution, elimination, 2 types of elimination. We could have combustion, both complete and incomplete, and finally esterification. So let's, I've got a couple little things to do, but I want you to practice first. Can you draw, this isn't a reaction, can you take the word ethyl methanoate and draw out the ester? Okay. There's no water here. And then you've got a reaction. Can you take butanoic acid and ethanol and write out a reaction and name the products? Right. So the answer to the top one, methyl, this is the alcohol part. The ethanoate is the acid piece. So I'm going to kind of mirror the wordings. I'm going to put the alcohol piece on the left in one possible answer. So Meth is 1 carbon. So then I can go to the O. Okay. And then I'm ready to deal with the acid piece. Ethanoate is, F is 2 carbons. And it's the acid piece that has the C double bond O right next to the O in the middle of the chain. Okay. That double bonded O will never be at the end. It's always right next to the O in the middle. Okay. And then I have to have 4 bonds in all our carbons. So that's one of 2 things you might have drawn. Okay. You could have done the mirror image. Okay. You could have put the acid on the left and the alcohol on the right. So you could have put the F, acid, first. That's the piece that has the double bond. And the alcohol has 1 carbon. Both of these are equally correct. I would assume most of you probably did the left version, but some might have done the right. Now, you weren't asked to do a line structure, but we need to deal with these. No new rules. We just have that O in the middle. That's a little new. So we've got 2 carbons. So that would be just a line. So there's our 2 carbons. Then we need to go to an O. I've got to put a line and then put an O at the end of that line. So our 2 carbons are there and there. And then we got a dash to an O. The carbon next on the left of the O has a double bond O. So we put 2 lines and an O coming up to tell the reader where that double bond is. Then on the right, we've got 1 carbon. So I'm going to drop my pen next to that O, but there's an O there. So that's really a 0 carbon count. I go over 1, and then I can lift because I just want a methyl. Those 2 line segments leading into the O have no carbons at them. So that would be the line structure or the mirror image of that for methyl ethanoate. Again, our carbons are there, there, and there. The 2 and the 1. So I'm going to take those green circles out. And I'll just pause and make sure everybody has a chance to finish the bottom one, and then that answer will go up shortly. Be done. So answer for the bottom one, reaction, and name it. Benzoic, butanoic acid, 4 carbons, double bond O, OH. I'm not going to color code this one because you're not going to see them color coded on tests. Plus ethanoic acid. Like you might see on an exam, the hydroxyl group may not necessarily be close to the carboxy group, but you have to realize it's the O of the alcohol going to connect there. So we're going to need an acid catalyst, strong concentrated acid. We're going to have 4 carbons with that double bond. Then we get to the alcohol. That's the O from the hydroxyl group of our alcohol. Then we get 2 carbons. Fill in our H's, not too fast that you put an H underneath the C double bond O. There's no bonding capacity left there. Make sure we don't forget our water. And this should be now balanced. The name comes from the alcohol piece first. So that's 2. So that's ethyl. The acid segment forms the second part of our name, 4 carbons. Butane would be the alkane name, but we don't put the last E and we go O8. Now these names can get really tricky if they're side groups, but we will be doing non-branched examples. Okay. We'll leave branched examples, side groups on the butanoic acid for post-secondary. So that's the bottom answer. One last example to do. Nothing super new except for dealing with how to name benzoic acid. That drop the E to the alkane name isn't going to work here because benzoic acid isn't based on an alkane. So we're just going to see a slight tweaking to the name of our ester. So methanol. Again, we saw phenol. You have to be aware of that name. You have to be aware of benzoic acid. It's an aromatic hydrocarbon or hydrocarbon derivative with that carboxy group off a 7th carbon, not off the ring. Now our connection sequence is the same as I've been doing. This is where drawing that arrow from the alcohol O to the C of the C double bond is going to help us connect this right. So there's our double bond, or our lone pair on our oxygen, and that's going to be attracted to the negative. Will go to the positive of that carbon. So we've got 1 carbon from the alcohol. The black O stays. We connect to a blue carbon with a double bonded O. The blue OH is going to go away as part of our water. And then we have our aromatic ring. I'm going to use a line structure to show the aromatic ring and get my water in before I forget. I know I keep saying it. It's so easy for you to forget the water. It's easy for me. A lot of lessons I teach by accident, I'll forget the water once. I'm being really careful today and trying not to forget the water, and I haven't yet. Name the alcohol black piece. That's not new. That's methyl. The benzoic acid, we're going to drop the oic acid and add O8 in its place. So probably what you would guess, but it's not going to an alkane name, dropping an E and adding O8. So this is an esterification. Esters tend to have smells. Both the methanol and the benzoic acid have hydrogen bonding. So they're very soluble in water, so they tend to stay in the water. The ester has dipole-dipole forces, but no hydrogen bonding, not super soluble. So that ester will come out of the water and you can smell it, or it'll come out of the gum or the bubble gum and you will smell that ester. Some smell like bananas or peaches, and some are more pungent, like nail polish remover. Okay? So some are nice, some aren't. Okay? So that's the end of esters. One last little bit, it tends to show up as a wrong answer a fair bit, and I at least want you to see it. It is discussed in your textbook, hydrocarbon cracking. Cracking, which is done a lot in the oil industry, is taking a long hydrocarbon, heating it up under strict conditions, careful conditions, and breaking it into multiple pieces. because the smaller pieces are maybe more valuable than the longer pieces. Now, you can't predict the exact sequence, but you know the atom count has to match. If you take a C20, you could break it roughly in half. I broke it in a 9 and 11 piece. There were 42 hydrogens at the beginning, so there has to be 42 hydrogens between the two pieces. So if you see some hydrocarbon, an alkane or alkene, and it's broken into two smaller pieces, that is cracking. Okay. Now, where you're most likely to see this, fractional distillation shows up on every diploma, and there'll be a picture of it, and often fractional distillation is one of the answers, and hydrocarbon cracking, this is one of the wrong answers to identify that diagram. Okay. So just if you see this word, particularly as a wrong answer, or maybe this year's diploma will have this on it, you can identify hydrocarbon cracking.